Okay, gang, this is the continuation of the two-way ANOVA calculation video, and I just want to illustrate, the calculation of p-values and so on and so forth. And I want to get into to doing this problem with R as well. So what I did, I went ahead and made the calculations, and I found out that the sum of squares for factor A was 297.5. and the sum of squares for the error was 383.70. Let me show you how I did these calculations. So at the end of the day, there's 2 out of 4. So, well, actually 2 out of 5, but once you get to 4, you can clearly go back to the fact that, the sum of squares for A plus the sum of squares for B plus the sum of squares for the interaction plus the sum of squares for the error has to be equal to the sum of squares for the total. So if you can get 4 of the 5, you can easily get the 5th one. So what I did here, the sum of squares for A turned out it's not that bad because there are only three column means, actually 3 row means in this case. So when I did that, I just sat down and plug and chugged and put it in my calculator. It took me about a minute. And I ended up with 297.37. Guys, in my calculations, I used the mean of 36.27. Even though I rounded this to 2 places, when I plugged it in my calculator, I used 36.275. So, if we're off a little bit, that's cool, just rounding errors. Now, sum of squares for the error, I cheated. I used Excel, and I'll show you how I did this. It's kind of clever way to do massive calculations. All I did was in Excel, I had the measure and then I had the factor. Well, from earlier, I saw that the cell A1B1 had a mean of 34.5, so I just filled in 34.5 for each of those. The cell A2B1, which again, if we'll go back to go back earlier. Actually, way back earlier. Okay, so for example, let's just choose something random. A3B2 was 35.95. So A3B2. So A3B2 was just, again, 35.95. Next thing I did is I used the fill down feature of Excel, which worked really nicely. So what I did here is I came in and took A2, which is the cell count, minus D2, which is the cell mean, and squared it up. And I just did a fill down, got all those values. And then in the end, I just came in and just summed it up. Okay? So that's the way that I cheated. I certainly don't think it's cheating. It's just actually makes more sense than sitting down and doing this by hand on your calculator. Now the whole reason I want to illustrate that is I want to illustrate the calculation of the F statistic and the p-value. So if we're filling out the ANOVA table, what is this row going to look like? Well, we know that the sum of squares for A was 297.37. And we know that the sum of squares for the error is 383.73. Now the next thing we have are the degrees of freedom. And the degrees of freedom for the factor A is just the number of levels minus 1. And the degrees of freedom for the error term are AB times n minus 1. So we're going to have factor. Guys, I do not know why this won't go there. So what's going to go here will be the levels of A times the level of B times n minus 1. So we're going to have degrees of freedom of 27 there. You think these calculations are bad? Wait till we get to something like the Mankova design. This stuff gets completely crazy. All right, gang, the next thing that we need to do is come up with our mean square. And the mean square is just the sum of squares divided by the degrees of freedom. So that's always easy to take care of. So this is going to be 148.69. And then 383.73 divided by 27 is 14.21. Now, the F statistic for factor A is just going to be the mean square for factor A divided by mean square for the error. If we were doing the F statistic for factor B, it's going to be the mean square for factor B divided by the mean square for the error. When we're doing our interaction, mean square for the interaction divided by the mean square for the error. But right now we're just focusing on, what goes in for the F statistic for A, and it's going to be 148.69 divided by 14.21. So this is going to give us 10.46. Now, remember, our F statistic follows the F distribution. And this is the F statistic for factor A. So what? A minus 1. So in our situation, this is going to be F of 227. I think, right? Yeah, F of 227. Now, and again, our F statistic is 10.46. So our p-value is going to be really easy to calculate here. So we're making our calculation from the sampling distribution, the F distribution, degrees of freedom 227, and we need the area to the right of the curve for 46. Well, guys, R can do that for us. Very quickly. And it works with PF. Now remember, PF is going to give us area below. Whatever value we put in for our F statistic, it's going to give us below. So we need area above, so I need to do 1 minus. So 10.46, comma 2, comma 27. So my p-value here is going to be 0.00043. And I'm writing this down so I've got it once I go back to the blackboard here. Okay? All right, gang. The rest of it would just be about persistence and perseverance and a whole lot of patience too. If we wanted to go ahead and fill in the sum of squares for B, the sum of squares for the interaction, and make all the calculations. Ultimately, guys, we're going to end up with 3 F statistics and 3 P values because we're going to examine the interaction and the main effects. Okay, so guys, a little bit of terminology there. A, B are called the main effects. And obviously A cross B is called the interaction effect. So what I want to do now is I want to illustrate using R what we actually get here. Okay, so looking at this hypothetical example of factor A and factor B, what would we do once we ran this out? Now I'm going to close this down, and because I was actually in doing some other stuff, and I'm going to open R back up. All right, so set working directory. Get my data. Attach my data. And look at my data. Now, I know factor A and factor B. I pointed out earlier that we need to set that as a factor, but I know from experience that I know it's going to treat those as categorical data, so I really don't need to do that. So if I'm ready to get in and just take a look at what's going on here, I'm going to run my ANOVA. So I'm just going to call it my model. And I'm going to run AOV, measure, over, factor A cross factor B. Now really, when you do your interaction term, it's all that you need to do in R. You don't need to include the main effects because it'll include that automatically. So we hit that. My undergrad students flip out. Man, when they do something like that and they don't see an output, they think they've done something wrong. Actually, it means you've done something right. If you hit model, you're going to see that you get the sum of squares and degrees of freedom for your terms. Now, notice that the sum of squares matches up pretty well for the factor A and the residuals, and so do our degrees of freedom. All right. Now, to get a better look at the ANOVA table, we can do summary of model, and then you see you get in a situation where the degrees of freedom, sum of squares, mean square, F values, and your probabilities, I mean your P values are given. Okay? So what do we look at? When we get something like this, what is our tunnel vision? Our tunnel vision is right here. Is the interaction effect statistically significant? If it is, and the literature is really varying on this, guys, but so this is kind of Darbo's school of thought. If your interaction is statistically significant, we want to look at multiple comparisons and look at profile plots. And those things are complicated as can be. There's going to be one complete video just on profile plots. And again, if the interaction is statistically significant, I want you to ignore the main effects. If the interaction is not statistically significant, like we have here, I want you to rerun the model without the interaction effect included. So in this situation right here, we don't have a statistically significant interaction. So the next thing I would want to do is I would want to rerun the model, and I'm just going to call this model 2. And I want to look at measure over factor A and factor B. So I'm not looking at the interaction here, and this will just give me the ANOVA without. So if I do model 2, notice that I get an ANOVA output without the interaction effect. Now when I look at this, my factor A is statistically significant, telling me that the difference in measurements is attributed to factor A. Factor B is not statistically significant at the 0.05 level, but it's close enough that I think it would probably warrant some investigation. Now, let me show you what, let's say that we did have an interaction effect that was statistically significant. The thing that I would want you to do from there is I would want you to then conduct a post hoc and create a profile plot of marginal means. So let me show you how to do that. Post hoc here we would run a Tukey HSD, and I want to run this over the model that includes the interaction, and I just called that model. Okay. Now what this does, it comes in and gives us pairwise comparisons, and it's pretty natural to just come in here and start trying to locate the p-values that are less than 0.05. So in this situation we see that A2B3 and A1B1 are statistically significant. Now in this situation, you know, what the heck does that mean? It tells you that if we go to A2B3, and then what's happened here? All right, it's kicked me out. Let me get the... All right, gang, let's go back. Okay, so cell means here. What we're seeing in this output is we have statistically significant interaction between A2B3 and A1B1. So A1B1 and what was it, A2B3? It's seeing these two means as statistically significant. Come on down. And since there's no other difference, for some reason it's attributing that difference to A2 and A1. So it's not finding actually the interaction to be statistically significant. Obviously because we didn't reject, right? Now, something else I would want you to be able to do is to get an interaction plot. And to do that, we would run like this. And interaction plots tell us a lot if we can figure them out. Now, I don't like the way this one lays out at all. Because first of all, it allows us to compare our levels of A1 across factors of well, I should say our factors B across A1, A2, and A3. We found statistical significance. You know what? I think this is actually going to give us a better plot. Yeah, it actually does. Now, if we look across B1 and B2, it's not finding statistical significance there, but it did find statistical significance for A1, A2, and A3. So that would take some more investigation. I'll tell you what I'm going to do. The next video that I put up, I'm going to go through a very, very, very thorough, starting with elementary, at the elementary level, I guess, how we actually look at a profile plot. Because this one's really complicated. You can see why, or at least I can see why B was almost statistically significant and A was, and it's really clear why there's no interaction. So let's start from let's build our house not on sand but on a good solid foundation. Before we get into interaction plots, let me put up one complete video on how to examine interaction plots, okay? And then we could generalize, because this is a pretty complicated one to figure out. You can you know, if you deal with these much at all, you can clearly see where the statistical significance is coming from. But guys, more about that at the proper time. Okay? So there's illustration pretty complete. Getting into the calculations, how we get our p-values, f-statistic, and so on and so forth. The profile plots are going to get a little crazy, but I think I need to allow about an hour video just on that. So I'll go and give you all kinds of different scenarios and show you what these things are going to look like. So guys, it's going to be a short video, so enjoy it. This is going to be one of your shorter ones probably. So.